Imagine our entire planet. Now imagine 1,000 of them. That is exactly how many Earths you could pack inside the volume of Jupiter. Yet, despite this enormous presence, there is no solid ground to stand on. Any explorer attempting to land would find only an endless, pressurized descent through layers of swirling gas. For decades, our understanding was limited to distant observations. In photos like this one from Voyager 1, Jupiter appeared as a beautiful but inaccessible void, a world too hostile to ever truly inhabit. But in orbital mechanics, volume is secondary to mass. This much material packed into a single sphere generates a gravitational pulse so intense that it dominates the space around it for millions of miles. Jupiter functions as a gravity engine, an invisible power source that actively dictates the orbits and evolution of the entire solar system. Gravity pulls inward on the planet's heavy atmosphere, crushing gases together until they generate immense internal heat and some of the most powerful magnetic fields in the solar system. This energy fuels the Great Red Spot, a high-pressure storm system wider than Earth itself. This diagram illustrates internal thermodynamics. Heat from the core rises, providing constant energy to the turbulent cloud bands. Without continents to provide friction, these winds accelerate to 400 miles per hour, allowing storms to persist for centuries. Scientists continue to monitor the storm's dimensions to determine if this constant gravitational pressure will keep the cyclone fueled indefinitely or if it will eventually lose its cohesion. The violent surface we see is simply the visible exhaust of this internal gravitational engine. Looking beyond the atmosphere, Jupiter's gravity anchors a collection of moons so large they function like a miniature solar system. This rhythmic stretching is called tidal heating. As these moons orbit, Jupiter's gravity physically pulls at their interiors, creating intense internal friction. On the moon Io, this friction generates enough heat to melt rock, fueling a landscape defined by constant volcanic eruptions. The same process occurs on Europa, though its surface is composed entirely of a thick, global shell of water ice. Tidal heating melts the lower layers of ice, maintaining a massive subsurface ocean of liquid water, completely hidden from the vacuum of space. While the environment directly surrounding Jupiter is a lethal corridor of radiation, the interior of Europa provides a stable, shielded environment warmed by gravitational energy. The solar system's most dangerous planet is also the primary energy source for what may be the most habitable environment beyond Earth. To understand the planet's largest impact, we have to look at the entire solar system and the swarms of debris that move through it. Jupiter acts as a gravitational stabilizer. Its mass intercepts inbound comets and asteroids, pulling them into its atmosphere or slingshotting them away from the inner planets. Orbital mapping shows many of these objects would have crossed Earth's path without Jupiter's intervention. Without this massive guardian, the inner solar system would be a much more frequent target for large-scale impacts, significantly altering the environmental history of the smaller rocky planets. This suggests that the long periods of stability required for life to thrive on Earth are a direct consequence of Jupiter's constant gravitational presence. Contemporary data describes Jupiter as a dynamic architect, a planet that exerts a constant, governing influence over the chemistry and safety of our solar system. The Juno mission is currently providing our most detailed look yet at the planet's magnetic fields and its deep, complex core. Maintaining a functional spacecraft in an environment with this much radiation and pressure is a significant technical achievement, representing decades of engineering and precise coordination. This work continues with the Europa Clipper, a mission specifically designed to investigate the chemistry of the moons being heated by Jupiter's gravity. This probe will allow us to finally determine if the conditions for biology exist in the liquid water beneath Europa's ice. As we move further into deep space, Jupiter remains a constant, a massive, silent force shaping the environment we are only just beginning to explore. It stands as the violent architect of our planetary history, and the primary reason we are now looking towards its moons to understand the potential for life elsewhere in the universe. Deep in the asteroid belt, hundreds of millions of miles from Earth, a massive silhouette emerges from the darkness. Its gravity reaches across millions of kilometers, capturing passing debris and stirring its atmosphere into storms the size of continents. This is Jupiter, the undisputed giant of our solar system. Seeing its scale up close challenges our basic assumptions about what a planet is supposed to be. To understand this world, we must quantify its physical presence. Jupiter is the largest planetary body in orbit around our Sun. This visualization shows the disparity in volume. If Jupiter were hollow, it could contain roughly 1,300 Earths. Across its equator, the planet measures 11 times wider than our own. Seen in isolation, Earth provides a baseline for scale, a small rocky marble in a vast vacuum. While Jupiter carries 318 times the mass of Earth, it is constructed from the lightest elements in the universe, hydrogen and helium. These are the same two ingredients that make up the chemical composition of the Sun. This combination of massive weight and star-like ingredients creates a structural paradox, an incredibly heavy object without a solid rock body. Despite its massive gravity, there is no solid ground here to land a spacecraft. A descent through the colorful cloud tops reveals an atmosphere that never ends. Instead, it simply becomes hotter, denser, and more extreme. Thousands of kilometers down, the weight of the upper atmosphere exerts crushing pressure on the hydrogen deep inside the planet. This pressure transforms the gas into a state called metallic hydrogen. In this form, the hydrogen becomes an electrically conducting fluid that swirls deep within the core. This fluid internal structure ensures that Jupiter's internal physics remain entirely different from those of rocky worlds like Earth. Returning to the visible layers, the chaos of the outer atmosphere becomes clear. Jupiter rotates faster than any other planet in the solar system, completing a full day in just 10 hours. This rapid spin acts as a planetary engine, stretching the atmosphere into racing bands that move in opposite directions. The friction between these bands generates enormous, ever-swirling storms that can last for centuries. Intense internal pressure and rapid rotational momentum combine to create a violent, unstoppable planetary system. Moving away from the atmosphere, we see the reach of Jupiter's gravity as it commands a vast system of rings and moons. Among these are 4 major worlds discovered over 400 years ago, each with its own distinct environment. Io is the most volcanic body in our solar system, with a surface continuously reshaped by erupting sulfur. In contrast, Europa is covered in a thick, cracked shell of ice that likely hides a liquid water ocean. Ganymede is a giant moon, featuring grooved terrain and complex geological structures that dwarf the planet Mercury. Callisto marks the edge of the major system, showing an ancient surface covered in billions of years of asteroid impacts. By maintaining this diverse collection of massive moons, Jupiter functions as the gravitational center of a dynamic, miniature solar system. Mysteries remain hidden deep beneath the clouds of the Great Red Spot, where lightning flashes through the dense gas. This massive gravity shaped the layout of the entire solar system, influencing the orbits of the planets we see today. To understand why our solar system looks the way it does, we must travel back 4 billion years, to the moment this giant world was born. Approximately 4.6 billion years ago, Jupiter did not exist. At the center of our neighborhood sat only a newborn sun. Surrounding that young star was a massive, violently swirling disk of hydrogen and helium gas, mixed with grains of dust, rock, and ice. In this early era, the solar system lacked any discrete planetary bodies. It was a region defined by random, microscopic collisions between drifting particles. This raises a central question. How did a cloud of dust eventually condense into the most massive planet in our system? To find the answer, we must move away from the intense heat of the young sun, toward the freezing environment where solid matter could finally begin to stabilize. This temperature gradient illustrates a specific boundary in the early solar system known as the snow line. At this distance, the environment became cold enough that water and other volatile materials froze into solid ice. Closer to the sun, the heat was too intense for these materials to remain solid. Without ice to act as a building block, A gas giant could not form in the inner solar system. Crossing this line provided the cold, stable environment necessary for Jupiter to begin its growth. In the frigid space beyond the snowline, billions of frozen dust and ice grains drifted through the disk, constantly bumping into one another. Because these particles were coated in ice, they possessed a sticky quality. When they collided, they fused together rather than shattering. These clumps compounded over time. Grains grew into pebbles, pebbles merged into rocks, and rocks accumulated into massive boulders of solid ice and stone. Eventually, this accumulating mass reached a critical threshold. The icy core became heavy enough that its own gravity became the dominant local force. Its increasing mass generated a gravitational pull that dominated the local neighborhood, dragging in any nearby debris that crossed its path. This solid core acted as a structural seed, anchored in an orbit where it could exploit the vast, untouched resources of the outer solar system. With a massive gravitational field established, the core entered a phase of runaway accretion. It began drawing in the most abundant materials in the protoplanetary disk, hydrogen and helium gas. Jupiter expanded at an immense rate, growing faster and larger than any other object orbiting the Sun. This schematic shows the resulting internal structure. The original dense core is now buried beneath thousands of miles of highly compressed metallic and molecular hydrogen. By devouring the surrounding gas, that small frozen rock was transformed into the gas giant we recognize today. As Jupiter reached its massive final size, its immense gravity began to actively reorganize the rest of the solar system. The planet migrated through the disk, encountering millions of smaller celestial bodies along its path. Its intense gravity caught passing space rocks, altering their trajectories. It redirected asteroids into new orbits, flinging comets toward the solar system's edges. By clearing out these orbital lanes, Jupiter dictated where smaller objects could safely form and survive. Without Jupiter's massive presence stabilizing the outer regions, the inner planets, including Earth, could have ended up in a very different configuration. Billions of years later, the chaotic energy of the early disk settled into distinct cloud layers. Today, Jupiter is a highly complex, fascinating world, defined by a powerful magnetic field and an extensive system of moons. Yet beneath those organized stripes, it remains a living fossil that still harbors the turbulence of the early solar system. This lingering chaos is most evident in a single, massive anomaly. The Great Red Spot is a centuries-old storm, spanning an area larger than our entire planet. To truly understand how this giant operates today, we have to look past its origins and dive directly into its most violent storm. This is Jupiter, and this swirling vortex is the Great Red Spot. To understand the scale of this system, consider its diameter. You could fit our entire planet inside the boundaries of this single storm. Within these clouds, winds reach speeds of hundreds of kilometers per hour, creating one of the most violent atmospheric environments in the solar system. On Earth, we track massive hurricanes that form over our oceans and churn across the globe. These terrestrial storms require a constant supply of energy to survive. When they encounter the friction of a solid landmass, that energy dissipates and the storm dies within days. If planetary physics dictates that storms eventually lose their momentum, why has this specific Jovian storm raged continuously for hundreds of years? The answer lies in Jupiter's composition. As a gas giant, the planet has no solid surface. Without continents or mountain ranges to crash into, there is no surface friction to sap the storm's rotational energy. Beyond the lack of friction, the storm sits between two massive jet streams moving in opposite directions. Acting like a planetary conveyor belt, they shear against the top and bottom of the vortex, actively feeding its rotation and preventing it from slowing down. The Great Red Spot is a natural byproduct of a frictionless environment, a vortex kept in motion by the very atmosphere that surrounds it. While the storm's rotation is mechanical, its distinct reddish hue is a product of chemistry. The storm acts as a massive elevator, dredging particles from deep within Jupiter's lower atmosphere and forcing them into the upper layers of the sky. Once these particles reach the top of the clouds, they are bombarded by intense ultraviolet sunlight. This UV radiation triggers chemical reactions that essentially bake the gases, changing their composition and color. While researchers are still identifying the exact chemical formula, the color is a direct consequence of the storm's verticality exposing deep gases to solar radiation. Even with a frictionless engine and a constant supply of chemical fuel, the Great Red Spot is not immortal. Historical observations reveal that the storm has been changing. This data plots its measured width from the 1800s to today, showing a steep downward trend. Scientists continue to monitor the storm because its ultimate future and its potential disappearance remains uncertain. This transition proves that Jupiter is not a static world. It is a dynamic environment where even the most massive features are actively evolving. Pulling back from the Great Red Spot reveals the full scale of the Jupiter system. The planet's cloud layers are the backdrop for a collection of extraordinary worlds orbiting the gas giant. These are Jupiter's moons, geologically active bodies characterized by subsurface oceans, ice sheets, and volcanic plumes. To understand Jupiter, we must look past the shifting storms and explore the solid, alien worlds caught in its immense gravity. When we think of moons, we typically picture something like our own, a quiet, heavily cratered rock locked in a silent orbit, long past its active geological days. But the environment around Jupiter operates by completely different rules. This is a massive, chaotic region defined by intense radiation and violent storms. The immense gravitational pull of this gas giant has captured a complex system of satellites. Among them are 4 massive bodies known as the Galilean moons, forming what is effectively a miniature solar system. Despite sharing an orbit around the same planet, these 4 neighbors possess wildly diverse landscapes. Their proximity to Jupiter has driven each one down a unique geological path. The search for life in this system is a process of elimination. By evaluating the extreme conditions on each of these worlds, we can narrow our focus to find the single most promising environment for biology. The innermost large moon in this system is Io. It holds the title for the most volcanically active body in the solar system. Its surface is a patchwork of yellow, orange, and black, entirely covered in sulfur and fresh lava flows. Massive eruptions are a constant occurrence here, ejecting material hundreds of miles into space. This relentless activity is driven by tidal heating. As Io orbits, Jupiter's massive gravity physically stretches and squeezes the moon's rocky interior, creating immense internal friction. Because its crust is violently melted and reformed on a daily basis, any potential for a stable environment is destroyed. Io is entirely too volatile to support life. Farther out from the chaos is Callisto. As the outermost Galilean moon, it sits in stark contrast to Io, a quiet, heavily frozen world. Without the extreme tidal heating found closer to Jupiter, Callisto's surface has remained largely undisturbed. Its dark, icy crust preserves a record of impacts stretching back billions of years, showing almost no signs of geological resurfacing. That distance does offer a practical advantage. It keeps Callisto safely outside Jupiter's deadly radiation belts, making it an ideal target for future human outposts. But physical safety does not equal habitability. Callisto is geologically dead, lacking the internal heat required to spark biological chemistry. Moving inward, we find Ganymede, the undisputed giant of the Jovian system. Its surface is a complex mix of ancient dark regions and lighter, deeply grooved ice. To understand its scale, you only need to look at the inner solar system. Ganymede is larger in diameter than the entire planet Mercury. Its massive size allows for a unique feature. Ganymede is the only moon known to generate its own internal magnetic field, driven by a convecting liquid core. Between that active core and the frozen surface, data suggests a deep liquid water ocean spans the entire moon. However, this ocean is trapped beneath dozens of miles of solid ice. Furthermore, the ocean floor itself is likely composed of highly pressurized ice rather than exposed rock. Because the liquid water is sandwiched between impenetrable barriers of ice, it is completely cut off from the moon's rocky core. Without access to surface chemicals or core minerals, the ocean lacks the nutrient mixing required to support biology. That leaves us with our final candidate, Europa. At first glance, it is a relatively small, bright sphere of ice, but it hides a compelling mystery. On Europa's surface, we don't see ancient craters. Instead, we see a reflective crust crisscrossed with thousands of long, reddish-brown fractures. These ridges indicate the surface is physically tearing apart. The ice plates are shifting, behaving exactly as if floating on an active, fluid layer. Beneath the frozen shell lies a global, salty, liquid water ocean. The scale of this subsurface environment is truly immense. Though Europa is smaller than Earth's moon, its ocean is so deep that it likely contains more liquid water than all the oceans on Earth combined. Crucially, unlike Ganymede, Europa's liquid water is in direct contact with its rocky mantle. This allows tidal heating from Jupiter to drive geological activity on the seafloor, mixing essential chemical nutrients directly into the water. Through this process of elimination, Europa emerges as the prime target for exploration. It possesses the water, the chemistry, and energy to support life. The lingering question now is whether the chemical building blocks in that dark ocean have already combined to form it. Far out in the deep freeze of the outer solar system sits Jupiter, a massive gas giant suspended in a pitch-black vacuum. Orbiting through this freezing environment is Europa. From a distance, it looks like a barren ball of solid ice. At first glance, a world this cold should be completely inactive. Yet scientists hunting for biological signatures have made this specific moon a primary focus of their research. Bypassing the distant view for a high-resolution analysis reveals that the surface is far from smooth. The ice is heavily fractured, a chaotic web of reddish-brown scars, ridges, and deep cracks cuts across the otherwise bright white exterior. Geologically, these specific formations tell us that the crust is continuously tearing apart, shifting and sealing itself back together. The ice is moving. That constant surface activity indicates Europa is a dynamic world, driven by something massive directly beneath its frozen shell. If we could plunge straight down through those fissures, bypassing kilometers of solid crust, we would cross into a lightless, fluid interior. Measurements of Europa's magnetic field and surface fractures point to a singular conclusion. The ice conceals a global, salty liquid ocean. Condensing all the ocean water on Earth into a single sphere and comparing it against the estimated volume inside Europa reveals the moon holds significantly more liquid water than our entire planet. In the search for biology, liquid water is the absolute first requirement. It is the universal solvent necessary for complex chemistry to occur. Possessing an ocean of this magnitude immediately elevates Europa from an icy outer rim satellite to a primary candidate for habitability. But water at this distance from the sun should freeze entirely solid. There has to be a mechanism keeping the interior liquid. That mechanism is a process called tidal heating. As Europa travels its elliptical path, Jupiter's gravity repeatedly stretches and compresses its shape. That physical flexing generates internal friction, producing heat deep inside the moon. This heat radiates outward, preventing the global ocean from freezing. If we follow that heat all the way down to the bottom of the ocean, the salt water meets Europa's rocky seafloor. The violent interaction between hot rock and cold, pressurized salt water drives chemical reactions, stripping minerals from the stone and releasing potential nutrients into the water. In complete darkness, Europa provides water, thermal energy, and active chemistry. The three required components for biological life exist in a single location. We have the models, and we have the surface data, but we must be precise about the limits of our current observations. Scientists have not discovered life on Europa. The objective right now is not to locate literal organisms. The goal is to verify that these specific deep water environments are chemically capable of supporting biology. To gather that hard data, NASA engineered the Advanced Europa Clipper spacecraft. Equipped with a suite of advanced instruments, the Clipper is designed to measure the exact thickness of the ice shell and sample the chemical makeup of the water welling up from below. Answering the question of habitability will rely on decades of these careful measurements and verified data gathered millions of miles from Earth. Europa gives us a single, powerful data point in our mapping of the solar system. It demonstrates that highly active, fluid environments can exist entirely hidden beneath solid exteriors. But the existence of this hidden ocean is dictated entirely by the gravity of Jupiter. The same gravitational force that flexes Europa's core also anchors the paths of objects moving through the outer solar system. By capturing or deflecting incoming debris, Jupiter potentially serves as a massive defensive barrier for the inner planets, including Earth. Studying this gravitational reach reveals how the gas giant defined the conditions that allowed our own world to remain stable. Look closely at the inner solar system, and you'll see a chaotic environment. Earth shares its orbit with millions of moving rocks, ancient comets, and debris left over from the birth of the planets. For centuries, a comforting idea has persisted: the belief that humanity has a giant cosmic bodyguard looking out for us. Because Jupiter sits between us and the deep void of space, it's widely assumed that it acts like an enormous vacuum cleaner, sweeping up dangerous comets before they can get anywhere near our atmosphere. Modern astrophysics, however, paints a very different picture. To understand what's actually happening, we have to look at sheer mass. Jupiter is heavier than all the other planets in our planetary neighborhood combined. That immense bulk creates a deep indentation in space, generating a powerful gravitational field that dominates the outer solar system. Any inward traveling comet is forced to interact with this massive field as it passes by. Mapping how those small bodies behave when they hit that gravity well is the only way to determine if Earth is actually protected. In 1994, astronomers monitoring rat space made a startling observation. A comet was on a direct collision course with the gas giant. Comet Shoemaker-Levy 9 had ventured too close. The immense tidal forces of Jupiter's gravity captured the icy rock and violently tore it into multiple fragments. Those fractured pieces then plummeted downward, slamming into Jupiter's dense atmosphere in a spectacular chain of rapid-fire collisions. Look at the dark impact marks left behind in the planet's clouds. These massive atmospheric bruises provided physical, visible evidence of a cosmic collision. Strung out across the hemisphere, each of these impact zones was large enough to swallow the Earth whole. To the general public, observing this violent event seemed to settle the debate. It appeared that Jupiter had taken a direct hit for the inner planets, proving the shield theory true. However, the objects that crash into Jupiter are only half the story. The real threat lies with the rocks that survive a close encounter. This is gravitational redirection. When a comet grazes a massive gravity well, its trajectory snaps onto a completely new path. Often, this slingshot ejects dangerous bodies from the solar system, but those same gravitational forces can also redirect objects inward. By simply pulling on a passing space rock at the right angle, Jupiter's mass can grab a previously harmless object from the outer rim and hurl it directly toward the inner planets. Jupiter acts as a chaotic, unpredictable variable in Earth's ongoing orbital security. When viewed as a whole, the solar system reveals itself as a deeply interconnected gravitational web. In scientific terms, Jupiter functions as the primary gravitational architect of our planetary neighborhood. Over billions of years, its continuous influence has managed the flow of cosmic debris and dictated the precise structure of the asteroid belt. It functions as an indifferent force of nature, dictating the structure of our entire system, regardless of human safety. Beyond its invisible gravitational reach, Jupiter hosts a complex, tangible planetary system of its own. The immense pull of the gas giant creates extreme, volatile environments nearby, fueling the hyperactive volcanoes scattered across its moon, Io. Right next door, that same gravity flexes the moon Europa, maintaining a hidden ocean of liquid water beneath a frozen, fractured shell of ice. Even with advanced observatories watching the skies for decades, our exploration of this massive system has only just begun. Jupiter will continue to challenge our understanding of physics and planetary science, reigning as the undisputed king of planets. Looking at the massive scale of these swirling atmospheric bands and the Great Red Spot, we see a world that has ruled the outer solar system for billions of years. Jupiter possesses a physical mass larger than all the other planets combined. For centuries, astronomers saw only a serene ball of gas painted with pastel stripes. We now know those visible clouds hide highly violent physics. To truly understand this giant, we have to stop looking at it as a solitary object. It operates as the center of a complex miniature solar system. Peeling back its visible layers reveals how this massive gravitational architect dictates the environment for an entire family of surrounding worlds. Our most powerful tool for peering beneath those impenetrable cloud tops is NASA's Juno spacecraft. On the screens inside NASA Mission Control, scientists track Juno as it executes daring, close proximity flybys, gathering precise telemetry on Jupiter's gravity and magnetic fields. This cross-section illustrates Juno's major discovery. The massive storms we see on the surface actually plunge thousands of miles deep into the planet's interior. As those deep atmospheric currents move, they generate one of the most powerful magnetic fields in our solar system. That intense magnetic field acts as a massive particle accelerator, trapping and whipping charged particles into a highly radioactive environment around the planet. Juno's telemetry proves Jupiter is a complex, violent engine, forcing scientists to rethink exactly how gas giants operate. Outward from that hostile center orbits a remarkable court of moons, which now offer our best hope for discovering new planetary environments. Through global coordination hubs like the ESO Mission Control Room shown here, scientists direct the JUICE mission, specifically designed to study these complex icy satellites. Looking closely at this detailed view of Europa, you can trace an intricate network of reddish-brown fractures stretched across a frozen surface. Below that shifting icy crust, scientific data points to a vast, churning liquid ocean, an environment that could hold the chemical building blocks for life. Further out sits Ganymede. This dark, heavily cratered terrain reveals an ancient world with its own complex history and potential subsurface waters. These oceans remain liquid because of a constant gravitational tug-of-war with Jupiter, creating internal friction that heats the moons from the inside out. The dynamic nature of these worlds makes them the highest priority target for finding extraterrestrial environments. With vast oceans located so close by, the logical question is whether human astronauts could ever travel to Jupiter to study them directly. This scale map illustrates the severe biological barriers. Beyond the enormous physical distance from Earth, Jupiter is completely surrounded by a massive, glowing field of lethal radiation. Those extremes turn the planet into a biological fortress, making human visitation nearly impossible. Because of this hostile environment, the legacy of our exploration here will rely exclusively on advanced robotic proxies, plunging into the unknown on our behalf. Jupiter is a planetary physics laboratory and a gravitational architect. The violent depths of the gas giant and the hidden oceans of its moons provide a physical record of how planetary systems are built and sustained. Our robotic journey at Jupiter will continue, but our broader tour of the solar system must press onward. Next, we travel to a world famous for possessing the most spectacular visual feature in space, the magnificent rings of Saturn.